And let's start with a short prelude and say that the typical toy problem that I'm going to speak about is the following model as it is described, which is quite standard statistical problem. And there are going to be many typos in this talk, but I don't think that there is any typo on this slide. So this is the problem. You have a sample of X, and I want to find a good estimator of expected value of Y. But let's see what I mean by that. And as a second part of the prelude, let me quote Louis Gutmann, which is a strange guy that was in my department, in the Department of Sociology, that said the statistician is somebody who understands data only when they are noisy enough. And he meant by that he is not a statistician, so he does understand the data. I'm not sure about the second part. The first part I absolutely agree with. So I'll start with a foundation, because I don't know how much of the real foundation of what is called foundation is really taught and known by the current day students. So I'll really start from more or less the creation of the world. And I'll start what is experiment and how people are describing experiment. So experiment seemingly is a triplet of random variable, family of density or family of distributions, and a space of parameters, or set of parameters. And the first question is, what is this mysterious theta? So Berger defines theta as the unknown quantity which affects the decision process, and it is commonly called the state of nature. So theta is the state of nature, which is quite presumptuous, but this is the definition. Then we observe the data, and given the data and the experiment, the definition of the experiment, we should conclude something, say something about theta. And we should report the evidence about theta arising from E and X. Formally, we have a class of actions. It can be the parameter space itself. It can be age 0, age 1, when we are doing standard testing problem. And the statistical problem seems to be find a measurable delta such that delta of X is a good action. In theory, and only in theory, there is some mysterious loss function, L theta delta X, and its expectation permits us to define what is a good action. Okay, so let's return to the question of this state of nature that we started with. Bickel and Doxam, in very untypical poetic style, write that models and parameterizations are creation of the statistician, but the true values of the parameters are secrets of nature. Our aim is to use the data inductively to narrow down in useful ways our ideas of what the true P is. The link for us are things we can compute, statistics. Lecam, the other side of the corridor, wrote, each element of the set theta represents a particular theory about the physical phenomena involved in the experiment. And the difference between these two quotes, which are both taken from introduction to textbooks, is, I think, very illuminating. And the question is, the real question that I want to ask is, what are we inferring about? Are we inferring about the true P, or are we inferring about the true theory about nature. D.R. Cox took the position that actually what we are doing of Bickel and Doxam, at least as I understand the quote, because for him, statistical inference, the only thing that it does for us is to carry us from some observations to conclusions about the population sample. We are not going beyond that. We should speak about the true populations. And if we go to another one of the relative old masters, we should differentiate between statistical conclusion and experimental conclusions. Statistical conclusions are restricted to what Berger and Wolford described. We have experiment E, and we are operating with this experiment, with this notion of ideal model, which is very, very nice. But the question is, how valid is a theory? And usually and always the true conclusion are much weaker than statistical ones. And both the statistician morale and integrity are tested. Just quoting. Do we admit this or not? So the real question is how much more we add. And I want to add another remark. Usually in discussion, this type of strange discussion about foundations of statistics, people differentiate between the scientists and the statistician. The statistician maybe has a model, but the scientists know the theory. So I don't want to speak about philosophy of science. I don't know anything about it, so I will not speak about it. But really, when I say statistician, I mean everybody that is doing non-deductive science, which means everything outside, probably theoretical physics and humanities. So everybody else that is doing science is under this definition, essentially, of statistician. And Brenner and Fraser claim that something is usually lacking in this very natural models that Berger posed. And in their terminology, which I'll probably adopt, you need some additives, some more. Particularly principles and criteria, all are invoked primarily to get an answer. And the question is that if the only goal is to reach the particular posterior, the fastest and most unequivocal route is to start directly with the posterior as a particular additive. So in some sense, the question is, do we do more than that? And let me end the introduction with something that we all know. That is, I guess, in one version or other, everybody that is teaching Stat 2 or Introduction to Statistics or anything with this title gives example which is very similar to this one. So in 1995, there was a paper with the title, Why Do Old Men Have Big Ears? It appeared in British Medical Journal. And what they found is that if you measure the ear length, then you can fit very nicely the regression model that says that the length is 56 millimeter plus 0.2 multiplied by age. which from this very precise regression line, we can infer that a newborn has an average ear length of 55.9 millimeter, and probably like Dumbo, they can fly from flower to flower, enjoy their day. So extrapolation within the model we know that doesn't work. The question, does it work otherwise? And do we do interpolation essentially whenever we are doing statistical, many times when we are doing statistics? Okay, so, and as usual, garbage in, garbage out. What goes in is found out, or is it? Okay, introduction. Statistical model, we said, is the triplet XF P theta, and I can ask three types of questions when I do statistics, at least as much as I understand it. What I call the induction is we see X, what can we say about unobserved X star, where X, X star are IID? What can we say about P theta? So that's just the generalization, the empirical generalization from observation to unobserved. But they are the same. When we try to do deduction, we go one step further. We see X, and we ask, what can we say about theta, the true state of nature? However, there is a bunch of very standard statistical problems, which I call their type of inference as transduction, in which we try to generalize beyond the sample. So in the way I put it, we observe X, there is unobserved Y star, which is very similar to the X star that was here. The Y star has a distribution that belongs to another statistical model, defined by family of distribution Q theta, and somehow we hypothesized something about the relation between theta and tau. And we ask what we can say about Y star. What we can say about Q theta, about theta. So all the questions above, but about something we don't observe even a sample out of it. So we try to infer from one problem and transfer this knowledge to another problem. I don't know who introduced first the term transduction into statistical or statistical-like terminology. I met it first in the book of Vapnik. The definition of transduction given there, unlike the previous one that was taken from OED, is that in logic, statistical inference and supervised learning, transduction or transductive inference is reasoning from observed specific training cases to specific test cases. In contrast, induction is reasoning from observed training cases to general rules, which are then applied to the test cases. And the distinction is most interesting in cases where the predictions of the transductive model are not achievable by this inductive step. Somehow you jump from one example to example, and they somehow added the sentence which are not related to this definition, but I just quoted it, that it even doesn't give always the same predictions. That is because everything is to a large extent arbitrary, and somehow they put it into their definition. This was taken from Wikipedia and other wiki sources. That is, this sentence as here appears in different sources on the net. If I quote a paper by Vapnik, then he said that transduction is inference from particular to particular. So basically, his model of transduction is that you have a set of observations, yi to yl, with access x1 to xl, and you want to guess the classification of the next k equal 1 typically observation without going into a model. We are interested in the classification of a particular example rather in the general rule for classifying future examples. So as a statistician, usually we are taught to learn the rule and then apply it. So transduction as defined by Vapnik, you don't need this intermediate step, in fact. Now, we all know that statistics is not only about doing estimation, and I think that the main contribution of statistics is not procedures, but understanding that procedures have error which is built into them. So the right way to express a result is not the point estimate, it's a confidence interval, but a confidence interval which says we really don't know whether what we say is true, but it's likely to be true. In many cases it is true. We have a confidence in what we are doing, but we cannot say anything about a particular object. But near the particular object there is a particular inference. We say we cannot say much about a particular inference. And a particular inference means that I cannot say something about what do I mean by particular inference? This model that led me from my observation to the prediction whether passive smoking is harmful or not. That's a particular inference. So it's not only the point estimated, it's before even I look on the data. There is a particular structure that I found in the data, and we try to say something precise, something about this in particular things that we have interest in it. And the problem is that unlike the particular object, which we can quantify quite precisely, the 95% confidence interval that says that this, if we apply to the same, use the same model over and over again, we'll succeed in 95% of the cases. We cannot apply this structure that we use to infer anything about particular smoking to any other particular smoking, because there is only one phenomenon like that. I don't know how to generalize it. So we have two errors here. One is very limited to our particular problem, which we cannot say anything like 95 confidence interval. Okay, I'll speak about mainly two models, the prediction in time series and semi-supervised regression and classification. I'll try to argue what I see as the problems there. If I'll have time within, let's say, the 45 minutes, I'll say something about causality, but not really much. Time series. Time series is, we see a sequence of points, and we want to generalize. It's very similar to what Hume saw. He saw the regularity of the sunrise, or the regularity of a cause and effect. And one would appear ridiculous who would say that it is only probable that the sun will rise tomorrow, or that all men must die. Let me just say one remark about all men must die. It's pretty much according to our experience, except that to the best of my understanding, most people who ever ate ice cream still are still living today. So probably we are quite safe if we try to conclude from the past experience. Ice cream, as much I was able to to understand and to check appeared around the 18th century or something like that. So we are quite, yeah, some.
It's also true for statisticians.
Yeah, that's for, that is, yes. So, but the problem is, okay, so what is the statistical problem with time series? Because many people here in this audience are doing time series analysis. Okay, so let me start with a claim which will look you strange, and I'll say exactly next slide something which almost the same, but I claim that it's completely different. And so suppose we observe y1 to yt, which gets real values. We observe y1 to yt. Can we predict yt plus 1? Predict means build a confidence interval around it, around the value. So I don't mean predict, give a precise value. Just predict. And I believe, and I know that people think that it's strange, that unless some additives are assumed, you cannot do it. Absolutely cannot. What do I mean by additive? We can assume that y1 to yt plus 1 are IID. So that's very easy, then why the prediction would be just the average. We assume that there is some Markovian model structure that I defined here precisely, just to write something down. And then, again, we have a natural prediction. But nothing observed prior to the time t tell us that this model are valid, these additives are valid when we are going to t plus 1. And these assumptions are not for the statisticians to make, and everyone that does empirical science is here. Okay, so now let's look at another problem, completely different. Suppose now that we have y1 to yt, let's say interval 0, 1, and we want to predict yt plus 1 using its path, y1 to yt, and suppose that the predictor is good if the, let's say, the square distance between prediction and two values is small, and then under some minimal conditions this problem is easily solvable. In fact, there exists good deterministic predictor, so I even don't need to assume that there is a stochastic structure here to be able to solve this problem. It is so good that it works nicely when yt depend on the yt's themselves depend on the algorithm used to construct the predictor, so you cannot cheat it even, this estimator. So it's really wonderful. So the question is, so where is the difference between these two slides, which everything looks very similar, except there are two things. First of all, in the slide I made one, I looked on a particular yt plus 1. Here I'm looking on y small t, there it was a big T, capital T. So that's one big difference between the two slides. And to be on the safe side, here the range was a real line of the y's, and here it was restricted to 0, 1, or to anything like that. And this ensures me that catastrophes cannot happen. Here catastrophe can happen, we saw last year, and we looked on a particular prediction for a particular event, a singular event. Okay, so just to say that, not that I forgot my math, I'll do some technicalities as an interlude. So how can I construct an estimator so carefully that it's really almost assumption free? So the trick is to construct an unbiased estimator. So that's the first trick. And how can I construct unbiased estimator and recall that I'm using a methodology that is known to the constructor of the time series. So he will pick the y that will make my estimator as bad as possible. And yet I can do it unbiasedly. And variations on this were done by many people. So one construction that I would like to outline start with, okay, I'm not be really unbiased, I will be almost unbiased. And basically I look on a grid with k points, or 2k points, probably 2k points, very dense, quite dense grid, and take t to be some large number, very large number. And the procedure is more or less based on the following structure. I'll stack to a decision C sub j, and I'll stack to it until I accumulate enough data to say this is wrong. But I need to have a real large data set that tells me something is wrong here, and then I move quite slowly. And I move only one step right or one step left. Formally, I describe it here. I'm looking on, so phi I sub I was the definition I had. I start to accumulate observations, look on the average of the new observations with the past decision with a lot of weight given to it. T is a very large number, until the average is out of the small interval of phi I. It will take a lot of time because T is large, so as small t is, before small t is at least of the size of capital T, the mean will hardly move. And then, when I'm getting out of this interval, I'll move either to the left or to the right. And this will be our next decision. And then I can say that here it is written technically, I don't think it's not important, that under the above strategy, the distance between the true values and the true mean and the estimator would be pretty small. So k is large number, t is much larger than k, so everything is here very small. So usually my prediction is very close to the true mean. And if I want now to do it to return to the prediction problem, the scheme is to do the same, but condition on any estimator that you have, any time-based methodology can apply. You can get a predictor, and then doing the scheme that I described to unbias it and make it proper. So it will work reasonably well if the time scheme can work. Otherwise, I'll be at least always unbiased. So this will be the best I can do anyhow. So this is a standard compound decision approach. So basically, I moved from a decision to a compound decision approach. That is, I don't measure y hat t plus 1 with respect to itself, but with respect to a large set, capital T sets of predictors. And the compound decision approach saved the analysis because it really moved us from a particular inference about y capital T for the very particular capital T to a general inference about the whole sequence. And as I said before, I avoided the catastrophes. If catastrophes can happen, all this process will not work because the one particular, everything will depend on the one particular predictor, which will be very bad. Okay, semi-supervised learning. What we have here is a simulated set of observations, plus and minus, and I want to divide the plane to an area where I'll predict that the value is 1, and one that I'll predict it to be blue, and one that I'll predict it to be red. And I don't know if anybody of you can see what is going on here. Somebody can guess how we... No, by the way. Okay, so now the trick is that I'll add, again in the simulation it's very easy, I'll add unclassified observations. So the yellow points are 2,000, why it says that strange number, I don't remember, 2,000 observations which are unclassified. They are not zero, I don't know whether they are 0 or 1, but the red and the blue points were taken from the same distribution, except that we observed the y. Now I guess, most of you will guess what is a base predictor, and the base predictor is really this one. So this is what is called the semi-supervised classification problem. And formally what we have is small n, a pair of observation x's and y's. And we have capital N unlabeled data. So we have small n labeled data, data x's with a label, and we have many, maybe even infinite, and for all practical purposes, infinite number of observations which are unlabeled or unclassified. Now this is a very typical situation, if you think about it, and if you didn't meet it in the past. The examples are when X is recorded by fast electronic instrument, while the labeling is done by a human operator. An example would be satellite pictures of terrains or military targets. So satellites, you accumulate infinite number of pictures, but most of them nobody looked at them, and certainly nobody labeled them. You may look on email records. Most of them you just analyze technically, but some of them human operator read and decided whether they present some criminal or terrorist activity. Another example is when X is a routine medical examination that is done on the thousands per day. But to know the label, you need a real careful, expensive analysis. For example, it needs a postmortem. So, which is more expensive and harder to get because most people eat nowadays ice cream. So let's look on this model. The optimistic point of view says that if X has a density H, I basically can tell you what is a label. So for example, Y equal 1 most likely when H is small. And if H, the density is large, then Y is more likely 0. So basically I don't need the labels at all. I can just look on the density. And as it's written here, it looks funny. But if I will tell you that I have two clusters of X's, one here and one here, then most of us will tend to say, okay, so probably Y equal 1 here, Y equal 1 here, and Y equal 0 here, or vice versa. But it must be related to the label. So we have cluster, nice cluster, so they must be related to the labels. But this is something like that. The semi-parametric point of view, which is where I started, says something completely different. Suppose that we have this xy, which are pair of xy which are IAD. Suppose we have some semi-parametric model, x is a distributed age. Here there is a small typo. The theta shouldn't appear here. Why whenever I move the mouse, it is, okay. The theta shouldn't appear here under the p. So py equal 1 equal a function of x, parameterized by parameter nu, and h nu belong to some Cartesian product of h or h times nu, capital nu. Then the semi-parametric bound for estimating theta, which is some smooth function of nu, is the same whether the distribution h of x is known or unknown. Since by the unlabeled data we cannot know anything else but, at most, the distribution of h, this type of term tells me that I don't need the classified points, because the unclassified points can at most tell me what h is, no more than that. So, in other words, to be in the semi-parametric spirit, the unclassified sample doesn't carry any information about theta. Okay, let's look on example where things are basically hidden. The structure here is something like that. The interval is divided to in something like a Markovian process. If it wasn't normalized, it was Markovian process, but it's normalized. But it's divided to large interval and small intervals. So, the model says that on large interval I get observations, and they are always either 1 or 0. So what you get here is a picture that you observe. So the green lines are the intervals. So you have a few relatively large interval, and between them you have small intervals. The labeled data are the circles, the blue and the red. The blue are 0, the red are 1. And if you try to construct the non-parametric regression or any predictor, you are quite dead. You don't have enough information here. However, if you assume this structure, if you have labeled data, a lot of labeled data, which are here again the yellow dots, and since you have a lot of data, it became one big line, then it's very easy to find the intervals and to see where there are points and there are no points. And since if you know the intervals, you can construct the predictor, then this estimator will work, and you can solve the regression problem or the classification problem only because you have unlabeled data. So what we have here is the following situation. The classification error of estimator based only on the unlabeled data is very close to half. It's not half, it's slightly better, but very close to half, because you really don't have enough data. The classification error of an estimator based only on the labeled data is half. Okay, I switch between the two. No, sorry, I read it wrongly. As it written is true. You cannot do anything based on the unlabeled data. You can do very poorly based on the labeled data. But if you combine the two, you get estimation error, classification error, which is very close to 0. Half just to be on the safe side, half is just the worst you can get. But it worked because the way Py given the conditional probability of y equal 1 given x was constructed was very strongly tied to the way the support of x is constructed, and we and I knew it. And the question is it really different from assuming a direct relation between P and H. Let's go to another type, variation of this theme. A common practice, and this is really common practice, that if we have two with double O, many variables, is to reduce the number of variables using PCA. The logic is that if you have the correlation between x1 and x2 is very close to 1, we don't need both of them. We can retain only the average, ignore the difference, and if we have more than two variables, then PCA is a natural way to find structures like that we don't really need everything, and we can reduce dimensionality. And this reduction in dimensionality was done using only the X observations, no Y's in this stage. I want to do regression. That can work sometimes, and sometimes it doesn't. So Y may be in fact a function of the difference between x1 and x2, or the mismatch between them. And since when I prepared these slides, I was waiting to the eyeglasses that I'm having on my nose now, I was in this concept. So, for example, if x1 is the optical power of the lenses the patient needs, and x2 is the optical power that he actually needs, they are highly correlated, usually, because the optometrician is not that stupid. But if what I want to measure is something related to headache, then the small difference is what makes a difference and not the absolute number. And I can build other example where to the first sides, if things are correlated, highly correlated, but really what's factor into the psychology or biology, whatever, is a mismatch and not the average. However, as I'm not that pessimistic, because collinearity is not really a problem from prediction. What I want to do is prediction, collinearity is not a problem. If I use lasso-like techniques, P much larger than n can be held, as long as there isn't a good approximation with small number of non-zero coefficients. So the issue is not how many variables I can use, but how many variables are really needed. So then the preprocessing does make sense, because what it can give me is a set of small number of variables, and I can add them to the rest of the original variable, to x1 to xp. So I can add the output of the PCA done only on the axis as variables to the regression line, but keep on the side the old x1 to xp, so I have many more variables, including some of those that I got from the PCA, and then if the PCA step happen to be smart, it will be useful. And if information was lost, in fact, in this PCA step, I can regain it back from the axis. At least I didn't lost all information that was in the axis and doesn't exist in the Z's. So semi-supervised learning can be done as long as it is done carefully, and as long as we don't really believe in the model that somehow we took out of nowhere to apply to the data. Okay, let me say very fast go through these slides. Counterfactual causality, and I gave the exact definition I found in the dictionary, which is very strange to me, but as a definition, but it serves me. I like it in this particular example. As a dictionary, I think it's wrong, if I may say so. The counterfactual theory of causality that goes to, I guess, Neyman, Heckman, Rubins. Probably I learned it from Josh Angrist, but I leave it to you, so I'll not repeat this theme of bashing him. So this is very, to my taste, a very strange model that people take it so patiently. So the model more or less says something like that each individual is characterized by two outcomes, YC and YT. The outcome, if he belongs to the control condition, and the one if he belongs to the treatment condition. Of course, everyone can participate either in the control or the treatment condition. And the causal effect is the difference between YT and YC. And only one of them is observed, and therefore I can write the outcome in this equation. And only YT, TI, and XI is some confounder, are observed, and I cannot observe YC or YT, but I'm looking for the difference. So I can estimate it, but the real problem is usually, and everyone agrees on that in real life, if it's observational studies, T is not independent of the Y's, and therefore this simple estimator that just look on the average will not say anything about the difference. Now, what I don't like, I don't like two things about this model. The first thing is that it uses heavily loaded metaphysics, which is very unnatural to very positivistic science like statistics. And I can use this terminology if it helps me, if it really simplifies the analysis, if it unifies the terminology, if it justifies in one shot Occamian step too many problems, then I can be happy with this terminology. But the X is not that sharp, and the razor is not that sharp, and I don't think that it solves anything. It doesn't help me if the treatment is continuous, and in most cases treatment are continuous, even if I measure it as either or, and look on their example, people are not either passive smoker or passive non-smoker, either study or don't study to an exam, either take the drug or don't take a drug. And then how do we have a continuity of counterfactuals? Where do we put all them? It will not save us. It doesn't simplify the terminology because we have a natural terminology, which is a conditional distribution. And we cannot even dispense the conditional terminology because we must use the conditional terminology in the analysis because we want to do everything conditioned on a covariate X, which is really what they are looking for. And in fact, all the techniques are based on conditioning on some random variable X. But the real problem with causality is that we are not interested in the question per se, but what is the distribution in the population, but we want to switch a model. And therefore, it is the most typical or most extreme transduction problem. And what do I mean by that? It is moving from a situation where people choose somehow randomly whether they take the treatment or the control, to a situation where we enforced on them to take treatment or control. And what we do then, that we want to move from the joint distribution in one model to a sort of conditional distribution, but it's only a sort of conditional distribution in a completely other model where things are even not the same, it's completely different because we don't have the same sigma field and we don't have the same distribution. We move, and this is essentially what is done under causality, and somehow we want to do it. So there are, I think, two vocal lines of causality research. One was done by the people I mentioned before, starting with Neyman, and the other one is done, is centered in Los Angeles around Pearl. And he is very extreme in his claim. First of all, I believe that causality is the only problem of statistics. Everything else is not interesting. So if I say that transduction appears in statistics, he believes that everything else is not real. And then he says something very strong. There is nothing, which I completely agree with. There is nothing, so far I completely agree with him, there is nothing in the distribution function to tell us how the distribution would differ if external conditions were to change, say from observational to experimental setup, because the laws of probability theory do not dictate how one property of a distribution ought to change when another property is modified. And then he adds, and here I'm not sure how he does it, this information must be provided by causal assumptions which identify relationships that remain invariant when external conditions change. So basically what he says, in my terminology, is you have to assume the transduction. Somehow you see one observation, one experiment, and you have a method to infer from it on another setup, completely another setup. So I started with an example in the time series situation where the empirical based compound decision trick worked. When can we expect it to work, and is it related to this type of discussion? There were a few things there. We have a nice model, we have a post-factum verification, and we look for a general and not for the particular. Most causality judgment, more patient causality judgment are on the particular, and there is no post-factum verification that can tell us whether things worked in the past or not. And therefore, I don't see how this can be saved. So, if I summarize what I wanted to say, is it the induction, which is a generalization from sample to population, is a true domain of statistical theory. Deduction, which is going from sample to parameters of nature, is speculative, but legitimate. Transduction, going from the sample to a different particulars, from sample to a different model, is hardly legitimate. However, to be positive, generally speaking, careful statistical reasoning can work nicely on the average and not in particular. And I would like to add by my favorite statistical song by David Boudville. The first goal is to see the thing itself in and for itself, to see it simply and clearly for what it is. No symbolism, please. Second goal is to see each individual thing as unified, as one with all the other 10,000 things In this regard, a little wine helps a lot. The third goal is to grasp the first and the second goals to this universal and the particular simultaneously. Regarding this one, call me when you get it, please. Thank you. Did I? No, I'm not there.
I don't want to take anything. I didn't quite understand your kind of trick there on the time series prediction. The role of eta. Can you go into this slide, please? It looked like some kind of trick that you use also when you discuss super efficiency. And the other eta, this role of eta. Can you explain this a little bit more?
Okay.
Possible also then have an effect on the number of finite times on the next zero.
Yeah. Okay. Currently, the problem is here that was posed is like that. I have a time sequence x, and I want to predict the x, and I want to predict the expected value, to predict the next value. And you know, if you want to predict the weather and you want to be unbiased, it's very easy. Just take, assuming that everything is stationary, just took the Lagrange average and tell him that this will be tomorrow. So it will be a very poor predictor, but it will be unbiased. So basically, this is what I'm doing here. I'm predicting the next observation by the long time average. However, I don't assume stationarity. So therefore, I have to move slowly with the data. And that's what I'm doing. So I'm keeping a prediction as long as I decide about, I change my prediction and I keep it for a long time until the accumulated observation from the time that last time I changed my prediction have mean which is completely different from my current value. So basically, if the sequence will be stationary, then my prediction will be the long time average. But I permit it to change slowly. So that basically is the idea here.
Justification line was the problem. How did you exactly generate the blue and the red?
So basically what I generated here,
Actually, I was writing this my movement of my arm because I think this downward slow didn't move. So I'm
yeah, but you have to do something like that. Yeah, the first approximation, yes. You know, I could make these volleys deeper and then it would be harder, you know. But if you look, I don't think that that you can, and this is if we are speaking about empirical science, the one most important thing that I learned from my colleagues in mathematics, in biology, that apply to statistics is two definitions. One of them is the most typical example, and the other is the only typical example. But this is a typical example. So I basically look on this that I don't think, so it's really, I didn't play with it. So it was one run after I fixed the parameters and this is the data. I don't see, I know exactly what was done here. I constructed it myself and I still don't see what is going on here what is going on here when I'm looking on this picture. Yet, in this picture, suddenly things start to be clear.
interpretation, because I can think of many problems in economics, say, where the treatment is continuous, let's say, or at least multi-valued. And that function is exactly what you want to know. So, for example, demand function is exactly the potential outcome function. So the potential outcome is a function of the price, or an earnings function, or a variety of things like that. You're not asking about the whole set of distribution functions. The potential outcome function is the object of interest.
The expected value, as long as there is no noise, I agree with you. As long as the outcome is function.
You would like to know it without noise, but as long as there's noise.
No, as long as there is a built-in noise in this function. If your behavior is deterministic, if there is a function f which is deterministic that tells me that everybody, if the input is x, the output is y, I agree with you. If you believe in, I agree that the terminology is right. But if you believe that if the input is x, the output would be, not because of measurement error, because this is the individual property of this individual guy, is fx plus epsilon, and you want to tell me all the epsilon that he decided about them in advance, I can think about extreme cases where this is useful.
Maybe a little wire would help.
Yeah, okay.
There's one question. In many prediction problems, the analysis basically assumes at some level exchangeability. It sometimes can be masked or buried in different modeling situations, but some sort of exchangeability seems to be necessary in order to make predictions. And would that be a fair generalization of the different models?
Yeah, yes, that's fair. If you assume, but what I want to say is that many cases you don't believe in exchangeability, and still you do. So it's not all statistics is in what I take, you know. But as I say, even time series I can, in my extreme position, there are situations where I believe that things are proper and things that are not proper. But I don't enter into strange philosophical positions that like Hume that says, what do you think, that as a human being I worry about whether the sun will rise tomorrow? No, I know it will rise tomorrow. As a philosopher I have a problem with this. Well, so I'm not Hume, but
not everything will be exchangeable, but the predictions are all maybe always based upon that wishful assumption in some sense. Maybe making allowances for covariance, maybe making allowances for something else, but we cross our fingers and hope.
Yes, I say it works on the, generally speaking it works, but I don't know how on a foundation level I can quantify this. Generally speaking it works. Certainly, generally speaking it works, you know. We live longer than we lived 100 years ago, so somehow science works. So, okay. Yeah.
We have great experience with statistical methods and approaches, and I remember an article of Lehman, statistical science. It was, I think the title was "The Pendulum Will Swing Back." It was about the overweight of smoothing methods, dimension flexible methods, as Chuck Stone would say, or Bulko non-parametric methods versus classical 90 years in Lehman 50-60 type modeling. Can you, from your background experience, tell us, has it swung back the pendulum already?
Depending what you mean swung back, that is.
Because Lehman had two-dimensional regression lines in the future.
And in my apartment, in my home in Jerusalem, there are two people that are doing statistics, and there is another guy that is called statistician. And so the two people that are doing statistics are doing just a simple regression, and they are doing every day, well, on daily basis, the regressions, etc. things. And I think that they're doing right, you know. So if you ask me, they are doing the right thing. If you ask me, but yes.
Thank you. Very nice talk. So I have just a very simple question related to your saying God should be God out. So I know at least the conclusion from the discussion I have gone so far always based on two things. One is data, information you provide, and the other is your model assumption. No matter what you do one way or the other, we have to assume something to get another thing. So do you have a view in what way I could decompose my conclusion or my assumption, and in what way it would be my data inferred conclusion?
There are two questions. There is a not that interesting question, which is where we are really standing on our 2 feet, with is generalization from sample to population. The type of statistics that I'm interested in, the science that is done in science, is usually slightly different. They want to know. In many cases, it's different. It's not always. The problem is that whether you can look on the conclusion as a generalization of the sample. That's one thing. Then the usual answer is, it works, you know, you are too pessimistic. But then I wonder about the 95% confidence interval that we are so proud of it. What does it, or the 0.05 p-value that we are so proud of it. And the issue is not the 0.05 versus 0.01, the issue is, what do we mean by this number? So when people say statistical methods work, they mean it usually work. What is usually here? What is usual here? Can you quantify this usualness? I don't know. That is, it somehow, we say something very precise in a situation which is very unprecise. And yes, there is my signature on a few papers like that. That is applied papers where the 0.05 appears. But can I stand behind it? I don't know. That is, I really, as I said, I try to understand.
So in a lot of your discussions, not necessarily here, and you put a lot of emphasis on, let's say, prediction errors as exemplified by your concept of sparse system.
Yeah.
And in many scientific studies, we are not only want to predict well the outcome. For example, I not only want to classify disease correctly, I also want to know the mechanism behind it, that is, which gene is actually responsible for the disease. But not that we do it not too far. I just like using your example, I'm on the screen. So suppose you ask me for the yellow ones to classify, I will certainly find one of maybe nearest neighbor classifiers, which really give me just as well the job that you are doing. You are already for generating the data. Maybe just as well, but certainly for as a scientist, I would like to know what is the data generating mechanism. And in order to understand that, I have to assume something. So I just want to see what your general comment, because this is really put a lot of emphasis on the prediction outcomes.
first of all, I think that the science, unlike medicine, is not about prediction, but about model. And results in science, I believe, are not important in some sense. And what do I mean by not important? That the typical paper, even if it appears in Nature, doesn't make much of a difference on science. There is a lot of accumulation in an informal way of inference that science is built out of it. That it gets a lot of papers. So that's the general picture. And what is created is a general picture, I believe, and consensus. And therefore, all these small errors are somehow swallowed into the general picture of the poem I read. And that where so science has no problem as long as you are in general. But my problem is the particular. And the particular is a one-time decision, the patient in it, a conclusion from a specific research. And either global warming, either not. People do believe in it, I think, slightly too much in any particular experiment. So, I don't know. That's beyond my understanding or field.
A really short question. Please comment on Bayesian philosophies. For instance, if I understand correctly, in Bayesian philosophy, you have some priorities and then you observe the data, and your priorities are updated into the posterior, and therefore it's consistently, it's philosophically consistent. Understand correctly, which solves the induction problem more appropriate according to Zalman, 1976.
I don't really want to enter into it. I would say only one thing. Consistency is a very big property. Yes, if you are happy, if somebody is happy with what he believes in, whether it is in his prior or in his God, let him be happy with it. What can I tell you? That's, by the way, exactly where the main issue is where did you take? What is the source of your belief? Whether it's God or is it prior? Now, this is an illegitimate question, and therefore I don't know how to answer it.